Like many developers, I love working on code performance, getting deep into a problem, measuring, profiling, tweaking, squeezing out every last drop of juice from my code. As a Rails backend developer, I don't get to do this very often, but last year I worked on this project where performance was key. And working on that project, I learned some interesting lessons. This is a talk about assumptions. First of all though, hi, my name is Daniel and I work for GoCarless. We are a payments company based in London. Now, as you probably noticed, I'm not originally from London, I come from Argentina, so in case you were wondering, that's the accent. Now, before I get into the interesting part of this talk, I need to give you a little bit of context about the problem that we were trying to solve. GoCarless is a bank-to-bank payments company, which means we're sort of an API on top of the banking system. When you're a payments company, your customers expect you to always be available, just like they expect their electricity to always work. So for us, uptime is critical, and among other things, that means having good metrics for our apps is critical. One of the main tools we use for this is a metrics server called Prometheus. We love Prometheus, but we had a pretty big obstacle trying to use it from Ruby. Now, Prometheus basically gives the history of what all of your metrics have looked like over time. And to get those numbers, Prometheus will periodically hit your app asking for them. So in order to have metrics, you're going to have your web server that, in addition to running your app, is keeping a bunch of counters in there. Say, for example, how many HTTP requests it served, how long they took, how many payments were taken in different currencies. Prometheus will hit your app every few seconds asking for those numbers, and your app will return something that looks a little bit like this. Now, Prometheus also has libraries that help you do this. These libraries run inside your app, and you use them to declare your metrics, set their values, and when Prometheus scrapes you, they automatically generate this output in a format that you can use. And there's one of these libraries for all the major server languages. There's one for Go, there's one for Java, and of course there's one for Ruby. And for most languages, the story pretty much ends there. But in Ruby land, and by the way, also in Python land, this is a little bit trickier because Ruby and Python have a global interpreter lock, or GIL, which doesn't let your code run in multiple threads at the same time. Because of this, our web servers are usually not multi-threaded. This doesn't parallelize very well. Instead, in Ruby, we tend to use separate processes. Processes don't share memory, and everybody can happily run in parallel, ignoring each other. Now, the way this works is, when Unicorn starts, it will load your app, and it will fork itself into a master orchestrator process that's listening to requests, and a bunch of worker processes that are actually working on them. When a request comes in, the master sends the request to a worker that is free, and then it takes that response and sends it back to the client. This system works great. It scales really well across cores, and is how most Ruby web applications are running in production. But for the Prometheus use case, this is a bit of a problem because now that we have multiple processes and they don't share memory, which was the whole point of having them, each process will have its own internal counters. When Prometheus polls and asks for your numbers, the master process will send that request to some random worker, and that worker will report its numbers. But this is never what you want, because this number is only a partial view of the system. What you want is the global view of all of these processes added together, but because these processes don't share memory, there's no way for any single worker to see the counters in the other workers to be able to add them. This is by design, and is the main reason we use multiple processes, but for the Prometheus use case, this is a bit of a problem. And so, since the Prometheus Ruby client doesn't really support this multi-process aggregation, that means most Ruby projects that want to use Prometheus basically can't. And we definitely had this problem. We were using Prometheus, we wanted to have metrics for our main application, and we couldn't. And it wasn't just us. This has been the case for quite some people for quite a while. So we decided we would rewrite this library to solve this problem plus a few other issues that it had. But there was one more thing to consider. The Prometheus maintainers really care about performance for these libraries, because instrumentation should be free for your app. If you want to increment a counter inside a tight loop, for example, you should be able to do that and not even notice it. And buried in that long discussion in the 2015 GitHub ticket, we actually had a target. One of the main maintainers said, basically, that incrementing a counter should take less than a microsecond. Now, another maintainer of the gem basically went, yeah, you can't do that in Ruby, which guy number one's replies very recently, I mean, surely Ruby can't be that slow, right? And this leads to one of my favorite answers ever. I guess there's a reason people like running C extensions. Now, to store our numbers, we're using hashes instead of just plain integers for reasons that are going to make sense a little bit later. But what this means for now is that when I say increment a counter, it means reading and writing a value in a hash. And according to this exchange, this either could or couldn't be done in 1 microsecond. Now, I don't know about you, but if you had asked me back then whether you could do this in a microsecond, I had no clue, because I have no intuition of Ruby performance at this level. This is such a tiny scale compared to my usual experience that I really have no idea how long something like this takes. What I mean by this is that my entire Ruby experience for the last decade has been on the back end of web apps. So I'm used to a world of performance that looks a little bit like this. Imagine that this here is a second. This is 1,000 squares, 1 millisecond each. As a web programmer, this is how I see the world. Time exists in boxes of milliseconds. There's nothing smaller than that. So I'm running my web app and a request comes in. There's a couple of milliseconds that are taken by Unicorn, RAG, Rails, I don't even know, but before it hits my code, I just spent about a couple of milliseconds. Now there's a user ID in session, so we're going to hit the database to load that user. It's a well-indexed table, so it takes only 1 millisecond. The page we're loading is actually a list of orders for these users. So we hit the database again to load those orders, and we hit it one more time to load the items for those orders. Then we hit it a bunch more because we had an n+1 that we didn't know about. Oops. We check a couple of feature flags in Redis, which is super fast, but it's still at the other end of the network cable, so it's about another millisecond. And then we take all of this information and we render a view, which is actually quite big, so it takes a while. So that was what, 60, 70 milliseconds? That's reasonable for a Rails app, right? That's maybe on a good day. On a bad day, might look a little bit more like this. But this is basically my daily life as a Ruby developer. This is where my intuition works. These are the things where if I need to care about performance, I have a rough idea of how long things take, and I know where to look. But for other developers, this is very different. If you're a game developer, for example, you live and die in 16 millisecond buckets. If your game is going to run at 60 milliseconds, you get 16 milliseconds per frame, non-negotiable. And in those 16 milliseconds, you need to process your inputs, run your AI, your physics, your collision detection, all of the game logics, take all of that info and render a lovely frame. And if you miss the 16 millisecond boat, you skip a frame, your game stutters a little bit, and then thousands of hungry gamers will shout at you on Twitter. As a Ruby dev, I actually find the strictness pretty terrifying. And if you're a high-frequency trader, you're just dying of laughter right now. I mean, 16 milliseconds is an unthinkable luxury. If it takes just one entire millisecond, you're dead in the water. You can't even play this game. So the point I'm trying to make here is that what's fast and what's slow is really very relative. I mean, you have some people over here that are trying to get memory to be in big chunks all together so the CPU caches are full and you shave some nanoseconds, where I'm over that end of the spectrum, right? I'm trying to maybe not hit the database too much. The difference in scale is insane. And this is something important to keep in mind when we're talking about performance. Some things that to me, as a Ruby developer, are amazingly fast. Somebody that's writing drivers inside the kernel can't even think of using them because of how slow they are. So keep that in mind when somebody says that something is fast or something is slow. That is literally meaningless without a context. But we don't think about this most of the time. We just go with this is fast, that is slow, and we internalize it as if it meant something. Now going back to our original question, can we do that in 1 microsecond? Well, as I said, I'm used to these sorts of timings. For the most part in my work life, time exists in millisecond boxes. I cannot care about anything that takes less than a millisecond. I have much bigger fish to fry. So when you ask me, can you do this tiny thing, just increment the hash in a microsecond? Microsecond? That's this much. In case you can't see that very well, it's that tiny red dot over there. So if you ask me, can you do this tiny, tiny thing in this tiny amount of time? I have no idea. I live in milliseconds land. But we have two opposite opinions here. Surely we can figure out who was right? And here's the fun thing. They both kind of were. Let's go measure and see what we find. First of all, even measuring this isn't very straightforward because when the thing you're measuring is this tiny, the measuring itself is a significant part of your runtime. But if you happen to work around that, you're going to find out that you can do this about 12 times in a microsecond, which is great. It's well within our budget. And that's it, right? We have an answer. First guy was correct. Ruby isn't that slow. You can totally increment the hash in less than a microsecond. Except, in our case, it's not that simple. Now, as I mentioned before, we're talking about storing these numbers in hashes instead of integers. But why? Why are we using hashes? And the reason for that is you don't generally want one value for your metrics. You want more resolution than that. For the example of payments, you don't just care about how many payments you took, you might want to see how many in each currency. So we have this concept of labels. Each counter is tagged with these key value pairs that we call labels. And we store these counters in hashes where the key itself is a hash with those labels. And that makes incrementing these hashes much slower than if the keys were constants, because when we try to find a value, we're now comparing hashes to hashes instead of constants to constants, which is much slower. Now, how much slower depends on how many labels you have. For example, if you have 3 labels, it makes it super slow. Now, even if we consider a best case scenario that has no labels, it's faster than 3 labels, but it's still 9 times lower than with a constant. And you'll notice that's already quite close to our budget of 1 microsecond already. And here, we're just incrementing the hash. In real life, we need to add some validation and some processing to these labels, and we're not even thread safe. In order to be thread safe, you have to put a mutex around this, and now we're at a microsecond and a half per increase, and we blew our target. So it turns out, in our case, guy number 2 was right. I mean, we can't do this in a microsecond. But what I think is more interesting is not which one was right, is that I really wanted an easy answer. I wanted one of these two to win. But reality is more nuanced than that. And this is what I'm talking about when I say that fast and slow are meaningless without a context. It's always more nuanced than that. Bottom line, we can't hit the target of incrementing our counters in less than a microsecond. We're already past it, and we're still in a single process. We still need to do a multi-process solution. But we shouldn't throw the baby out with the bathwater here. The important thing is that because instrumentation shouldn't affect your performance, we want this to be as fast as possible. And because this will impact lots of projects for lots of people, it's really worth investing a lot of time into making this as fast as we can, even if we can't hit the target. And so with that in mind, how do we share those numbers between processes as fast as possible? Well, we experiment a lot. I mean, at this point, we basically tried everything that we could think of, and I'd like to walk you through 4 of the experiments that we did. First off, let's make this real easy for ourselves. Ruby has this unusual data structure called the p-store. Basically, it's a hash backed by a file on disk. Every time you set a value, the entire hash gets serialized to disk. Every time you read a value, it's all read from disk again. And the file has a lock around it, so you can actually read and write the same file from multiple processes all at the same time. Everybody sees the latest data, and it will be safe. And if you think about it, that is exactly what we need, right? I mean, we have this global hash shared by everyone. All processes see all the latest data. We're done, which is great. But the question we had was, is it going to be fast? And they're really no, this is not going to work at all. Now, if we take a step back and think about it, like, what are we really trying to do here? And basically, we're trying to have a chunk of memory that is shared between different processes. As a complete side note, one of the great things about Go Carless is the amazing people that I get to work with. Now, granted, some of those people are trolls, but the trolls sometimes have good ideas. I mean, SQLite was probably not going to be the best way to do this, but he got me thinking. You know what's a great way of having a chunk of memory shared between processes? It's Redis, of course. Redis is basically that. It's a chunk of memory running in a separate process to your app. All of the processes can access it, and we all know it's super fast, right? So again, this sounded like exactly what we need, and actually the Prometheus library for PHP uses Redis for this same reason, so it's actually very promising. So I wrote the code to use Redis as backend. I was super excited because I knew this was going to be the solution. Fired up my benchmarks, and the result was really disappointing. I mean, it's slower than just dumping the entire hash to a hard drive every time. And I was kind of sad when this happened. Like, I thought I had the solution. But more importantly, how? I mean, how can it be this slow? Isn't Redis supposed to be super fast? But if you stop to think about it, it kind of makes sense. I mean, you talk to Redis over the network. Even if it's localhost, every time you need to touch it, you need to make a packet, put it into a socket, send it over, Redis gets this, opens it, parses your command, runs it, makes a response, packet, socket. There's a lot going on. Redis is really fast for a database. I mean, it normally lives in its own server. You talk to it over the network. And those 60 microseconds that we just saw, they're basically nothing compared to the network round trip. So it's really fast compared to other databases out in the network. But compared to other things that happen in your own machine, in your own process, like writing a tiny file, they didn't even have a chance. So as I've been saying, fast and slow without context are meaningless. Now at this point, I had no choice but to face the giant elephant in the room. The consensus from pretty much everyone on how to solve the multiprocess issue was that we should use memory maps for this. This is, for example, what the Python library does. But during most of the project, I was really trying to avoid them. I wanted to find a different way because I didn't know them very well and they felt a bit dangerous. You'll see what I mean in a minute. Now, what memory maps let you do is have a shared memory mapped file. Basically, the way this works is your process opens a file and maps it to some place in memory. And then if you read that memory, you get the contents of the file. And if you write to that page in memory, the file magically gets updated at some point later, whenever the kernel feels like it. But here comes the magic. If another process maps the same file, they both get assigned the same page in memory. So if one process writes to that page in memory, the file eventually gets updated. But you don't care about that. What you care about is that the other process can immediately read that same page in memory and see the new data, which is magic. And the other thing you also care about is that there's a file, but you're not directly writing to it. You're just writing to memory, so it's as fast as writing to memory, not as slow as writing to a file. And again, this does sound like the perfect solution. The only problem is mmap is a syscall. Do you know how you call a syscall in Ruby? You don't, you do it from C. Now granted, this thing, which has the most hilarious line I've ever seen in official docs, but it's not particularly useful for this. And let's say you actually manage to call mmap with it. Now you have a chunk of raw memory and a pointer to it. Now what? How are you going to read that from Ruby? So what we need is some sort of gem that is probably written in C. And I don't write C, I can barely read it. And I should definitely not be trusted to write C code that deals with a syscall that I don't know well, and it does some magic memory voodoo, which is going to run in production not only in my company, but in a lot of other companies. This is not going to happen. But fortunately, there's a gem for this, made by Tenderlove. And in order to use it, you basically make a file, and you initialize it to a certain size, say like 1 megabyte, and then you give it an M map. And then you have this M variable, which behaves sort of like a byte array. There's basically a bunch of magic that the gem is doing, but it looks like a byte array to you. And if you have a bunch of bytes to write, you then basically set a range on that array, and that'll do it. Now the tricky bit is turning the stuff you want to store into a bunch of bytes. And to do that, you use these methods called pack and unpack, which will turn your Ruby stuff into bytes and then back into Ruby stuff again. But if you've never heard of pack and unpack, don't look them up. Keep your innocence. It's really one of the beautiful things about Ruby that you don't have to know about this. Now, in our case, we have a float, and we want to write into this M thing. So we pack our float into bytes, which takes 8 bytes, and then we set those positions in the array, and we're done. And basically, that's it. Now, how fast is this? Well, if you remember, these were our options so far. M maps, which as I mentioned, I really don't want to use, are actually quite fast, which is a bummer, because now we're gonna have to use them. And again, it looked like we were done. And I thought that too, but as soon as I started using this more heavily, I almost immediately got one of these. Now, I don't know about you, but I had never gotten one of these, at least not one that was my fault. This is a seg fault, and it's precisely what I was afraid of when using memory maps. And here's the thing. One of my favorite things about high-level languages is not having to deal with this. Like, I don't want to have to deal with this. I don't know how to deal with this. I don't even know where to start. This is precisely why I don't do C. And also, this is a very obscure gem. Not many people need to do this. There's nothing in Stack Overflow. I haven't found almost anyone actually using it. So it's kind of hard to figure out what I'm doing wrong. But this is what I managed to find out. The problem seemed to be happening with the initial size I gave the mmap. That 1 megabyte wasn't enough. I had some code to resize it, and the seg fault only happened if that code had run. Which is perfect. I mean, we have no idea why it happens, but at least we can reproduce it reliably. And so what we do with these kinds of problems is just try random stuff until something sticks. Now, it took a while because I had no idea what I was doing, but I ended up making the seg fault stop. It was an elaborate dance of unmapping, flashing the file, closing the file, reopening the file, resizing it, closing it again, then reopening and unmapping it again, and somehow the seg fault didn't happen anymore. Now, if you have a problem, you don't understand the problem. You try random stuff until the problem stops happening, but you don't understand why it was happening or why it stopped. How confident are you that that's not going to happen again in production, in some random server, in some random company's mission-critical app? I really wasn't. I did not like this one bit. So we kept looking, and this takes us to our last experiment. With the memory map, we were basically working with a thing that looks kind of like a file, doing the kind of things that you would do with a file, which just happened to be doing it in memory, which is faster than normal files. But what happens if we ditch the mmaps and we just do this to a file? I mean, pretty much the only difference is that we need to call these functions to jump around and to write, and that's it. And the interesting bit here is that you're only writing the minimum amount possible. You're not marshalling and dumping an entire hash into a pstore. You're just doing one seek and writing 8 bytes. It's very efficient. And that's pretty much the whole change. And now we have no memory maps, no C, no seg faults, there's nothing fancy. It's just plain old boring Ruby writing simple bytes to plain old files in slow hard drives. But as usual with these solutions, how slow is this, right? And before I tell you that, I want you to visualize how slow disks are. I mean, we use Redis and Memcached famously because they're in RAM and not on disk. We use RAM drives and TempFS, so we can have things that behave like disks but are not as slow. We give our databases just gargantuan amounts of RAM so they can keep everything there instead of having to hit the disks because the disks are so slow. So how slow was this solution based on disk? Well, if you remember, memory maps were about 6 microseconds per increment. Files on actual hard drives were 9. Now this completely blew my mind. This is mad. And if we compare this to memory maps, we now have no external dependencies. There's no risky C code. There's definitely no seg faults. It's compatible with all editions of Ruby, like JRuby. It's 100% understandable by any Ruby developer. And most importantly, there's nothing in that code that keeps me up at night. All of this for just 3 extra microseconds? That was a complete no-brainer. And at this point, we were done. I mean, we ended up going with disk as our end solution because it was fast enough, And we think that the trade-off is more than worth it for the peace of mind that this brings us. And this is where this talk should end. I mean, we solved the problem with a fast, elegant solution. We got our code merged. We're now maintainers of the gem. And now people can actually use Prometheus in Ruby, right? Happy times. But this is a funny result, isn't it? I mean, memory is supposed to be many orders of magnitude faster than disk, thousands of times faster. And I'm telling you is what, 30% faster? What's going on here? Well, as I've been saying, it's always more nuanced than that. Now, there's a number of things happening here, but mainly, if you're used to performance of things that use disks, you're probably looking at this last number with a lot of suspicion right now. And you'll be right, because what's happening here is that I'm basically cheating. Now, it's a fair cheat, it works for my use case, but I'm still cheating. You see, actually putting stuff on disk is slow, but that's not what happens when your app writes to disk. When you tell the operating system to write to disk, the OS takes note of that and goes, yeah, all right, I'll get around to that at some point. But it doesn't actually write to disk. It'll do it later, at its leisure, whenever it happens to be convenient. And normally this is a problem for you. If you're a database and somebody sends you data, would you trust it doing the hammock to actually do it later? I mean, of course not, because when somebody trips on your power cable, you've lost the data. What you have to do is you fsync, which is literally saying, hey, those things I told you to do them now, I'll wait. And that is slow, because now you're actually writing to a disk. Now, if you're a database, sadly, you really care about this data that you're writing, so you're going to have to pay that price. But I'm just storing the numbers for this particular run of my app. And if my app gets killed, I mean, Prometheus has the numbers so far. Next run of the app starts fresh from zero. I don't care if that data stays. I only care about it while I'm running so that the different processes can see the numbers. But once I'm dead, whatever, I'm starting over anyway. Which means I don't have to wait for the data to actually get committed to disk. And now it's not slow anymore. Because when I'm writing to disk, I'm really just writing to the bit of memory where the OS keeps a list of the things that it's going to write to disk. Which is cheating, but it doesn't mean you can't do it. It just means I have this unusual situation where I can get away with pretending to use disks without actually paying the price for doing it. So is memory fast? Are disks slow? As I've been saying, depends on the context. So we've covered a lot of weirdly specific ground all over the place right now, but what is the point of me being here? What am I trying to say? There's this age-old saying about performance optimization. You've probably heard it. Measure before you optimize, because the thing that you think is low is probably not the thing that is actually slow. And we all know this, and when I was trying to figure out where the code was spending time, I definitely measured, and I found many cases where time wasn't being spent where I thought, like the saying, right? They were correct. But what I found in this project is that that's not enough. Now, as I said at the beginning, this is not a talk about memory or disk or microsecond files or hashes. This is a talk about assumptions. When we decided that the solution to a problem where we needed to do things really fast was to put stuff on disk, I was shocked. I was completely stunned. And the reason I was shocked is that, like everyone else, I knew that disk is really slow. In fact, if you told me before the project started that Marshall dumping a whole hash into a hard drive would be twice as fast as hitting a localhost Redis server, I would have laughed you out of the room, because I just knew that's not true. But here's the problem with these things that we all know. They're normally very simple. They're very memorable. They have to be if they're going to spread and stay in our heads. Things like Ruby is slow, or Ruby can't possibly be that slow. I mean, surely you can read and write a hash in under a microsecond. Now, can you? Yeah. Can we? No. I mean, we're doing something weird for good reason, and it's slow. Memory is fast. Disk is slow. Redis is fast because it doesn't use disk. Now, is it fast? Yeah, for the database, it's really fast. Is it faster than disk? No, it depends. The problem is that there's a lot of nuance around these simple truths, and it gets lost in the process. If you look at them up close, these questions aren't simple. They don't have straightforward, simple answers. And everybody that believes these things hasn't actually checked them in the context of the problem. I mean, of course not. We already know they're true. But the reason that's a problem is that having these things that we all know is going to make you blind to potential solutions that you would otherwise see if you didn't have that knowledge. Take this project, for example. It's not like initially we sat down and we discussed it and we discarded disk because we thought it would be too slow. We didn't even consider it. It didn't even cross our minds because implicitly we knew it wasn't going to work. No, I happened to land on this by pure luck. I mean, I happened to notice that the memory maps were opening a file anyway, and it would be easy to make them do the same thing without the memory maps, and so I tried it. But I didn't try it because I thought it would be an actual potential solution. I did it out of pure curiosity. I knew it wasn't going to work. I just wanted to see how much ridiculously slower it would be. And if I hadn't, to this day, I wouldn't sleep well, wondering when that segfault was going to hit in production in someone's server. So what I'm trying to say is, when you're trying to solve a problem and figuring out how to approach it, try to be aware of that filter at the back of your mind that discards options because you know they wouldn't work. Pause. Just look at those options. Why do you think they wouldn't work? Are you sure it's actually true? Can you do a little experiment? Can you measure it? Because there may be a really simple, quick solution that you're missing because it wouldn't work. Sometimes it does. Thank you.